Let's delve a little bit deeper into the ocean warming and ocean land warming contrasts. This is the ocean heat content change from 1960 to 2016. There are later studies showing that the accumulation of heat in the ocean is getting stronger and deeper. So this is going from 0 to 2000 meters in watts per meter squared, and you can see that it is gotten warm all the way down, especially in some places like the Southern Ocean. The land here is so much, but you can clearly still see the Arctic ocean heat content, and there are dynamic patterns. So obviously we will see this in air temperature as well. So you can already imagine, based on your knowledge of the thermohaline circulation, that this southern tip of Greenland, Iceland, Norwegian Sea, and the Labrador Sea cooling must have something to do with the Atlantic meridional overturning circulation. Not very easy to say exactly what it is, but definitely related to that. So ocean does take up more than 90% of the excess energy from anthropogenic activities, but the dynamics determine where it goes, especially with depth as well. But the bad news is that whatever is the process and whatever is the place where it penetrates deeper, quicker, deeper ocean all around are getting warmer. Okay, so you can see that in this plot as well, going now almost back to 1860. So you have to be careful about the data coverage, etc. But these are simulated with and without volcanic aerosols, and the uncertainties are shown here as well in these bars. So you can see that uncertainty is 50% at 1997. So one has to be careful. Without going into details, I want to point out that the upper ocean down to 700 meter is obviously collecting most of the excess energy, but you can see that over time the amount of energy in the 700 to 2000 meter range and 2000 meter to the bottom is also increasing. Okay, over time the plumes are growing larger, which means the heat is penetrating deeper and deeper. You think these are small numbers, but imagine the heat capacity of the water, depth of the water column, and the width of the basins. Take the volume of water, multiply by these watts per meter squared, and you will get amounts of energy that are really, really mind-bogglingly large. Massive amount of energy is being stored up in the ocean. So don't be fooled by seemingly small watts per meter squared or temperature ranges. Okay, so here is the temperature trend looking at depths. The uniqueness of the Southern Ocean is somewhat obvious here because it's a channel. The winds can keep churning the ocean and the warming can penetrate deeper. In fact, the wind-driven currents can go all the way to the bottom, whereas in the other basins, as the winds begin to drag, let's say, trade winds from this end to this end, amount of energy that goes into the ocean gets limited. Same for the westerlies. Only about 2 to 5% of the wind energy goes into the ocean here, but because this is a channel, much more wind energy can go in, but it also can get mixed down faster. And that heat is obviously going to inundate the Indian and Pacific Oceans. Atlantic is different because Atlantic is sending the North Atlantic deep water into the Southern Ocean and taking the Antarctic bottom water in, right? But within each ocean, you can see there are again dynamic patterns. So these are depths and latitudes going from the Southern Ocean to the northern tip here, which is about 25 north because the Indian Ocean is blocked off by the Asian landmass. Atlantic goes to basically the pole. Pacific basically goes to the Bering Strait. And you can see that there are dynamics which are involved. Nonetheless, you can see these isotherms that are drawn here. and you can see subtropical gyres converge water masses and push the heat down. The deep water formation here he takes the heat down as well, and so on. So circulation in the horizontal and vertical determine the dynamic patterns of warming in the ocean. Plus, again, to remember, a warm Indian Ocean, small temperature can be more important because it can drive the atmosphere. In the western part of the Pacific, tropical Pacific, waters are warm, so small temperature change can be still important, and so on. So you have to always remember those kinds of dynamic details. Let's add the ocean and land contrast to this. Now this is going from, sorry I cut it off, 1880 to 2020, looking at annual temperature relative to 1901 to 2000 average, showing again that the land warming is much steeper, especially since about 1980, but oceans are keeping up, and ocean land together is in the middle here. So ocean is down here, this is the atmosphere, and sorry, this is the land, and this is the land and ocean. Heat content difference makes a impact on the temperature warming, but remember, ocean has heat capacity. That's what is critical. Land doesn't have much memory, right? It's high heat capacity but low memory, whereas ocean has massive memory. So that can be also contrasted with this temperature trends going from 1990 to 2019, clearly showing polar amplification and lack thereof in the Southern Ocean. This is only for a short period, so be careful. But you can still see the land-ocean contrast. Okay, so if the ocean is warming less than the land, then temperature colder, higher pressure, warmer temperatures, lower pressure, you get a pressure gradient, and then you get winds, and then the coastal alongshore winds, which are critical for upwelling and so on, can get affected by this, sometimes referred to as the cowl effect, cold ocean, warm land effect. So that's why we have to worry about the land-ocean contrasts in heating associated with global warming. Obviously that feedback will play into other dynamics that will be important with global warming as well.